In this lecture we shall explain how to refute statements involving predicates and operations on sets. Consider the proposition for all sets A, B and C, the union of the intersection of A and B with C is equal to the intersection of A with the union of B and C. This is a false proposition, as we shall show in this lecture, and to refute it we shall give a counterexample. First, to get some intuition about the meaning of the set theoretic expressions on both sides of the equality, we construct Venn diagrams. To determine the union of the intersection of A and B with C, we first need to determine the intersection of A and B and take the union of the result with C. On the other hand, to determine the intersection of A and the union of B and C, we first need to determine the union of B and C and then determine the intersection of A with the result. The Venn diagrams suggest that the two set theoretic expressions yield different results, although we still need to figure out whether it is possible to choose the sets A and B and C in such a way that the areas determined by the two expressions are indeed different. Note, for instance, that taking all three to be empty would not work here. The conditions on A, B and C in this case are fairly simple and easily realized. It suffices to put something, for instance a natural number, in every region of the diagram. We can then simply read off the required contents of A, B and C. A should consist of the numbers 1, 2, 4 and 5. B should consist of the numbers 2, 3, 5 and 6. And C should consist of the numbers 4, 5, 6 and 7. Let's work out the values of the two expressions given these three sets. The left-hand side expression can be computed easily. First, we work out the values of the intersection, and then we compute the union. We find the set consisting of the numbers 2, 4, 5, 6 and 7 as the value of the left-hand side expression. The right-hand side expression can be computed in a similar fashion. But now first the union is computed, and then the intersection, resulting in the set consisting of the numbers 2, 4 and 5 as the value for the right-hand side expression. We can now produce the actual counterexample. It starts with the assignment of concrete values for the sets A, B and C, and then gives an argument why under this assignment the union of the intersection of A and B with C is not equal to the intersection of A with the union of B and C. The counterexample serves as a refutation of the formula with which we started the lecture. It shows that it is not the case that the equality holds for all sets A, B and C. One counterexample is enough to refute the formula, but to illustrate that a counterexample is often not unique, we shall provide another one in this case. Looking at the Venn diagrams, you may observe that there is a simpler way to expose the difference between the areas represented by the two expressions. What we actually need is something in one of the parts where the areas are not the same. We could, for instance, put a number in B and C, but not in A. This amounts to assigning the empty set to A and the singleton set containing the number 1 to B and C. A similar computation as before would show that the left-hand side expression is not equal to the right-hand side expression with the given values for A, B and C. In general, a proposition is refuted by means of a counterexample, and a counterexample for a universally quantified statement about sets should have the following two important ingredients. It should have a concrete assignment of sets to the variables involved, and it should have an explanation as to why this concrete assignment indeed refutes the statement. Perhaps you found the Venn diagrams already convincing as a refutation, but we urge you to always go one step further and present concrete assignments and explicit explanations as to why these concrete assignments refute the statements. This approach will pay off later when we're going to refute conditional statements about sets. In the previous lecture we have shown how to prove a universally quantified equality about sets. In this lecture we have shown how to refute such an equality using a counterexample. In the next lecture we shall introduce another important predicate on sets.